This video is going to describe ionic radii, so that's going to be the sizes of ions. We're going to start by comparing the sizes of ions, both cations and anions, to their parent atom, that would be the neutral atom. And then at the end we'll do a practice problem that relates all of the concepts that we've learned about different trends. There's a previous video on atomic radii which discusses the trends and sizes of atoms and trends we see when we look at the periodic table. So we discussed previously that the sizes of atoms increases as you go down a family because you're increasing the shell number of the valence electrons, and that's going to increase the size because the larger the shell number, the more distant it is from the nucleus. We also discussed the fact that size decreases as you go across a row or period, and that is because the outermost electron, the valence electrons, are still in the same shell if the elements are in the same period, but the effective nuclear charge is increasing as you go across because the nuclear charge goes up, and that's going to pull those outermost electrons in more tightly, so that will make the radius smaller. And we're going to do a practice problem at the very end that incorporates all of these ideas. We're going to start with this idea that cations, those are positively charged ions, are always smaller than their parent atom, the neutral atom from which they came. So you can see here A is comparing the radius of neutral atoms of the alkali metals, lithium, sodium, potassium, rubidium, and cesium. You can see that increasing size trend within that group of the aqua bars. And then you can see the corresponding cation, which is the purple bar next to it. The sizes of those ions are considerably smaller than the size of the parent atom. In some cases, like lithium, less than half the size. Now, this is also true for the alkaline earth metals. You can see not only does the trend in size increase down the group, that's group 2A, but also the corresponding cation is considerably smaller than its parent atom. So you can also see the trend here that if you compare sodium, neutral sodium to neutral magnesium, magnesium is smaller. Remember we talked about as you go across a period, magnesium is to the right of sodium on the periodic table. So they both have electrons in the third shell, 3s1 and 3s2, but magnesium has a higher effective nuclear charge, so it pulls those electrons in more tightly. So you can kind of see that trend here as well. Incidentally, the y-axis here is the radius, so that is half the diameter of the atom or ion. It's in picometers. Picometer is 1 × 10⁻12 meters. They could have used angstroms. We've talked about angstroms a little bit in class. That's sort of the unit that was created to discuss atom sizes, right? So an angstrom is 1 × 10⁻10 meters. If they had used angstroms, then the values there, 100, 200, 300 picometers, would be 1, 2, or 3 angstroms. So let's talk about why cations are always smaller than their parent atom. These are the parent atoms, lithium, sodium, and potassium. If we just look at the first 3 alkali metals, if we remove one valence electron, that's going to actually effectively remove the entire valence shell. So lithium goes from having a valence electron in the second shell that you see there for lithium atom, and we remove it completely, then now all of a sudden its valence electrons are completely gone, and its outermost shell is the 1s shell, just the first shell. So it's much closer to the nucleus. And that's also true for sodium. We lose that entire third shell when we remove the single valence electron. When we remove potassium's valence electron, it reduces down to just n = 3, a third shell. And so we basically remove the entire outermost valence shell when we convert these neutral atoms into their respective cations. That's also true for the alkaline earth metals. For example, we have magnesium and calcium here. Because they form +2 ions, you're removing both of the valence electrons for magnesium and for calcium. So magnesium goes to only having 2 shells, and calcium goes to only having 3 shells. So magnesium has the same number of electrons as sodium, but it has more protons than sodium, right, in the nucleus. Calcium is a full first, second, and third shell, so it basically has the same number of electrons as potassium. So this, I think, explains why cations are always smaller than their parent atom. Further, the same explanation is given below these graphs. It says cations are smaller than the corresponding neutral atoms There are two reasons, both because the principal quantum number of the valence shell electrons is smaller for the cations, that's the reason that we just discussed, and because the effective nuclear charge is larger. And we're going to talk a little bit more about that in a minute. Now, anions are always larger than their parent atom, and so you can see here the halogens with the teal bars being compared to their respective halide ion, fluoride, chloride, bromide, and iodide, and you can see that the halide anions are considerably larger than their neutral atom, and so we're going to talk about this next. So if we just fluorine atom, we have +9 nucleus, 9 protons, and some number of neutrons, probably 10. And then we have, for the neutral atom, we're going to have 9 electrons. So there should be 9 little red spheres here. If we form fluoride ion and give it a full valence shell, then we're going to add a 10th electron. And the reason that the fluoride ion gets larger is because that added electron is repelled by the other electrons in that valence shell. And that tends to push the molecule out. That pushes the valence shell to be larger. It expands the valence shell because of charge-charge repulsion, right? Remember that negative charges, like charges, repel each other. The same thing is true for a chlorine atom. If we add an extra electron in the valence shell to give it 8 in its valence shell, then there's going to be charge-charge repulsion with all of the other electrons in that valence shell, cause the chloride ion to be larger just due to expansion. If we go back to our image here, our graph, you can see anions, their description, anions are larger than their neutral atoms because of additional electron-electron repulsions and a decrease in the effective nuclear charge. So they're talking about the fact that the effective nuclear charge goes down. It has the same number of protons in the nucleus, but there's more shielding in effect because there are more electrons present. And we're going to do these practice problems next. Okay, so here's our practice problem number 1. For each set, put the atoms and ions in order from largest to smallest. Okay, so we have cesium, strontium, magnesium, and magnesium +2 ion. So we'll start by looking at the periodic table, right? So cesium is here, it's an alkaline metal. Strontium is here, magnesium is here, and then we're going to also include in that magnesium +2 cation. So as we think about the trends here, 3 of these are neutral atoms and 1 of them is an ion. And so we're going to start by thinking about our trends, right? So the trends for size as we go down a family is that size increases as we go down. And so cesium is larger than strontium because it has valence electrons in the 6th shell, versus strontium, which has valence electrons in the 5th shell, versus magnesium, which has valence electrons in the 3rd shell. And so this is the reason why cesium is larger than strontium, which is larger than magnesium. We need to add in magnesium ion, and then to do that we can compare magnesium ion to its parent atom. This is showing you the trend that size increases as we go down because of the shell number, and it decreases as we go across because the effective nuclear charge goes up. Barium we know is larger than strontium, and we know that that is larger than cesium, and we know that cesium is larger than barium. So when we compare the 3 in red, right, barium we know would be smaller than cesium, but we also know barium is larger than strontium. So if you know barium is larger in size than strontium because it has its valence electrons in the 5th shell, 1, 2, 3, 4, 5, sorry, 6th shell. If you know barium is greater in size than strontium, and you know that cesium is greater in size than barium, then you know for sure that cesium is larger than strontium. So you might have to put some things together that you know here to get the final answer, right? It's kind of like a puzzle. Now for the last one, we're going to compare magnesium ion to its parent atom, which is neutral magnesium. We know that Cations are always smaller than their parent atom, which means that magnesium ion is going to be the smallest of all 4 of these. So cations are smaller than the parent, which means magnesium plus 2 goes at the very end. Okay, so that is the final order. Now, instead of asking you to put them in order, I may ask you to circle the largest one and underline the smallest one. That just makes it easier to grade at the end, but for practice problems, sometimes I do them like this, where you have to list them from largest to smallest, like I've shown here. We're going to move on and do part B. We have chlorine, fluorine, bromide, and bromine atom. So again, we have 3 neutral atoms and 1 anion this time. So we're going to combine some ideas here. We're going to circle chlorine and fluorine and bromine. Now, these 3 are all in the same family, and we know that fluorine will be the smallest of these 3 and bromine will be the largest of these 3, because fluorine has valence electrons in the second shell, and bromine has valence electrons in the 4th shell. So the size increases as you go down because the shell number increases, gets further from the nucleus. So we can put the neutral atoms in order. And then the only one that's left for comparison is bromine and bromide. We know that bromide, the anion, is definitely larger than the parent because of repulsion in the valence shell. When you add that extra electron, the other electrons in the valence shell repel it. Due to charge-charge repulsion, the outer shell expands, and that makes the anion larger. So we can definitely list bromide first as the largest of these 4, followed by bromine, followed by chlorine, followed by fluorine. So I'm going to put bromide in here. Now, there are ways there are obviously sets I could ask you where you couldn't answer the question. If chloride had been in here, you wouldn't have been able to answer the question because you don't know if chloride is larger than bromine atom, right? So I would never ask you any that you can't put in order, and if I do that, it would not be on purpose. So you should assume that you can answer all the ones I give you. But you might have to put concepts together like we did here. Now this question asks us, number 2 asks us to make an isoelectronic series composed of argon and 5 commonly observed ions. Now let's start by talking about an isoelectronic series. Iso, the prefix iso means same. Electronic means electrons. And so an isoelectronic series is a series of atoms and or ions that have the same number of electrons. So it stipulates that argon is going to be in the series, so that tells you automatically that if argon is one of the atoms, is an atom in the series, and it's a noble gas, so it's not going to form an ion. So argon is in the series, so you know how many electrons you need. And then it asks for 5 commonly observed ions. That means that you can't just make up any ion you want. It has to be an ion that normally exists in nature. Okay, you can't just make up something. So let's start with argon and go to the periodic table, and we will see that argon is number 18. So if argon is atomic number 18, that means it has 18 electrons because it is a neutral atom, 18 protons and 18 electrons. So we're going to put argon in the middle because some of these ions are going to be cations, which means they're going to have lost electrons. Some of them are going to be anions, which means they've gained electrons. And so we're going to list them first, and then they are going to put them in order. We're going to put them in order from smallest to largest. So let's first let's create 5 more ions that can go on here. So it's got to have 18 electrons. We're going to go back to our periodic table. We need 3 anions and 2 cations. So anions are going to have gained electrons and cations are going to have lost electrons. We're going to start with chlorine. Chlorine, when it gains 1 electron, forms chloride, which has 18 electrons. And then sulfur, when it gains 2 electrons, it has 18 electrons. That's sulfide minus 2. Phosphorus will gain 3 electrons to form noble gas configuration, so that would be phosphide minus 3. All 3 of those anions have 18 electrons, so we're going to list those on here. Chloride, sulfide, and phosphide. Now we need 2 cations. Those would have lost electrons, and so if we move forward on our periodic table, to potassium and calcium. Calcium is going to lose 2 electrons to have 18. It'll be calcium plus 2. Potassium will lose 1 electron to have 18 electrons, and it'll be potassium plus 1. So we're going to add those back in here, potassium plus 1 and calcium plus 2. Now when we consider the sizes of these ions, that's sort of the next step. The differences in these, they all have the same number of electrons, which means that they're going to have the same shell number. And so the same sort of distance from the nucleus. But what's different about them is the charge in the center. So the number of protons is going to be different for all of these. So let's look and see how the different charges compare so that we can put them in order. The charge of the nucleus differs in all of these. Argon is plus 18, chloride has a plus 17, sulfide is plus 16, phosphide is plus 15. Potassium is plus 19, and calcium is plus 20. So for all of these, the one with the highest nuclear charge is calcium, which means that calcium's valence electrons is going to feel the strongest pull from the nucleus, and it's going to be the smallest of all of these, okay? Because it has a higher effective nuclear charge, it's going to attract those valence electrons more, it's going to pull them in tighter. The one with the smallest nuclear charge is phosphide, and it's going to have a plus 15 nuclear charge. It's going to be the largest because its nuclear charge is not big enough to attract those valence electrons the strongest. So the ordering here is going to be phosphide is on the right-hand side, it's the largest, followed by sulfide, followed by chloride, followed by argon. And then the smallest one is calcium, we already said that, and the next smallest one is going to be potassium. And I'm going to put these less thans in here so it's more obvious. So now this is the ordering from smallest to largest. Calcium is the smallest, phosphide is the largest. And it's all about effective nuclear charge. The number of electrons is the same, number of protons is different. Now, if I ask you why, I didn't ask you why here, but it's about effective nuclear charge. So if I do ask you why, then you would say something in the effect that they all have 18 electrons, which means they have the same shell number, but the higher nuclear charge pulls the electrons in more tightly for calcium, followed by potassium, followed by argon, etc. So I could ask you why, make sure you understand. Now number 3, the figure below represents the reaction of a metal and a nonmetal to form an ionic compound. Identify which sphere, green or blue, represents the metal and which represents the nonmetal. So remember that metals lose electrons to form cations, and nonmetals tend to gain electrons to form anions. We have also learned that cations are always smaller than their parent atom, and anions are always larger than their parent atom. So you know definitively that the blue sphere represents the metal which forms the cation because it gets smaller, and that the green sphere represents the nonmetal which forms the anion because it gets bigger. So the green one is the nonmetal and the blue one is the metal.